Assalamualaikum and hi all. Today we are going to learn a topic from the course of Mathematical Modeling, Chapter 2, Continuous Model Using Ordinary Differential Equations ODE. I'm Norazaliza Muhammad Jamil from the Center for Mathematical Sciences, University Malaysia, Pahang. The topic for today is Simple Population Growth Model or Exponential Growth Model. We'll try to understand the most basic example in mathematical modeling. The goal of this lecture is to guide students to learn how to do mathematical modeling, how to solve the corresponding differential equations, how to interpret the solution, and how to develop general theory. Background of the study. Mathematical model is applied to understand population growth dynamics for animal and human populations, for example, fish, bacteria, etc. In this model, we try to formulate the changes of population. We ask ourselves some big questions. Will the population increase? Will the population decrease? What is the trend line for the population? Not limited to human populations, the mathematicians also study the changes of animal populations such as fish, bacteria, penguins, rabbit, lion, etc. Many processes may be considered as compartmental model. The compartmental model framework is extremely natural, which formulate the process based on inputs and outputs from a compartment over time. In the case of population, the compartment is the world. The input of population occurs through births and the outputs occurs through death. What we are interested in is the amount of population in the compartment at any given time, or whether over long periods the levels are increasing or decreasing. We can think of the population as occupying the compartment, and the rate of change can be considered as the rate in minus the rate out. Thus, we have what is called the balance law. In words, rate of change of population size is equal to the rate of birth minus the rate of death. In every model, the underlying assumptions are very important as they will give the direction to the model. We make the following assumptions and then, based on this, develop a model to describe the process. Assumption number 1. The populations are sufficiently large so that we can ignore random differences between individuals. Each individual has an equal chance of giving birth and dying. Assumption 2. Birth and deaths are continuous in time. The third assumption is per capita birth and death rates are constant in time. Number 4. We ignore immigration and emigration. And the last assumption is the change of population at any time is proportional to the size of the population at that time. After we list down all the assumptions, we can model the formulation using an ordinary differential equation. Let x be the population at time t. The rate of change of population is transformed into differential equation dx dt. In formulating rate of birth and the rate of death, we use the assumption that the birth and the death are proportional to the population. So, we put a constant here, beta times x, and for rate of death, we put a constant alpha times x. And we have minus sign here. The minus sign is based on the compartmental model, input minus the output. The addition to the population is because of birth, and the reduction of population is due to the death. We then factorize the right-hand side of the equation. It becomes beta minus alpha times x. And let's introduce a new variable r equal to beta minus alpha. Hence, the equation is simplified to dx dt equal to rx. The parameter r is called the net growth rate, also known as growth rate or reproduction rate, which is the natural growth rate minus the death rate. We should have r is greater than 0 if the population is growing. And now we have obtained a differential equation for the population size xt. We need one initial condition to ensure a unique solution. We have a simple equation, dx dt equal to rx. For this model equation, we can solve it analytically. We can find the exact solution by using separation of variable technique. The solution of the differential equation is xt equal to x naught e to the power of rt. Clearly, this describes exponential growth or decay depending on the sign of r. When r is greater than 0, the model describing exponential growth. When r is less than 0, the process is exponential decay. Not all model can be solved analytically. It is based on the complexity of the equations. In order to solve complex model in this course, we will use numerical method embedded in MATLAB software. To obtain the numerical solution using the fourth order Ranskota method, let's code this program in MATLAB, and we will get the output graph as shown in this slide. To understand the behavior of the population over time, you can perform the simulation through the programming code in MATLAB. In MATLAB, you can change the command line for initial value, the growth rate, and time, and so on. For example, if r equal to 0.017 and initial value x0 is 5.3 billion, we can predict the population after 5 years, 10 years, 100 years, etc. How to know whether your model is reliable? How to validate your model? The model can be validated by comparing the model with the data. We compare the prediction with population sizes at previous time for which data are available. An example of the result is given here. Let's examine the resulting graph. The data is shown by black dots, and the model is represented by the curve. Obviously, the model matches with the data only at the beginning, not at the later stage of the time. The model is unable to predict the behavior at the later stage of the timeline, but you can always give justifications to your model. We can say, for example, in situation 1, the prediction appears to get worse the further back we go. One possible contributing factor towards this discrepancy is that the birth and death rates have changed gradually due to improvements in technology and changing attitudes. Another situation. Based on situation 2, the model appears to be in good agreement in the earlier stages of the growth, but for later times, the population levels out rather than continuing to grow exponentially. The cause of this is that the death rate increases due to crowding and competition for limited resources. In certain animal population, the birth rate decreases when the death rate increases. Another reasons are the growth rate r is treated as a constant, is only valid local in time, and environmental limitation is not taken into account. There is a need to improve the basic model for population. There are several other ways in which the basic population model could be extended. We can incorporate immigration and emigration. Also, we can include the harvesting factor in the population model. To summarize in this topic, we cover the following. Number 1, mathematical modeling through compartmental model. Number 2, we develop general theory and model assumptions. Number 3, we solve the corresponding differential equations. And number 4, we interpret the solutions. That's all for today. Thank you.